Okay, right now I'm in the middle of the third, I'm in 3.1, problem set 3.1 of this book, Discrete Mathematics with Applications. I'm going through these problems both for just viewers out there, but also just for me to help me solidify my understanding of this. Right now, I just finished 25 and I'm doing 26. If you don't understand, maybe check out previous versions of this book or just try to go along with it, but let's get straight into it. Okay, consider the statement, all integers are rational numbers, but some rational numbers are not integers. So, the ones that are colored blue are the ones with solutions in them, so that's usually the ones that I'll be doing so I can check my work. So this is a predicate. It's some sort of statement like x is a rational number or something. Let this of x be x is rational. Okay, in this case, so this, whenever this is there, this means x is a rational number. Let this mean that x is an integer. Write the given statement formally using only the symbols given here. Okay, so when you write the statement, all integers are rational numbers, but some rational numbers are not integers. Okay. So I would say, okay, so just starting with this thing, all means I'm going to start with a for all. So I have this doc here, which I've been writing my things in, so I write 26, and this is going to be part B. Now, so I'll start with for all, we'll say, yeah, fine, we'll say for all x, if int x, so this is if x is an integer. Wait, if is not allowed. Sorry, so I'm just gonna say int x implies that x is rational. So this is basically saying if it's an integer, then it's rational. Basically, being an integer makes it rational. So it's saying for any x value possible, now we're going to narrow it down to saying if it's an integer, then it's rational. That's this first part of all integers are rational numbers. But now we're going to say, I'm looking similarly to this, so we're just going to basically add a but statement. So let's go here and write, we can't do but. Guess for all x, integer x implies this. Now I'm going to actually put this in brackets because now I'm going to use an and. This is called an and statement. This is how I'm thinking. I'm going to use an and. So the reason I'm putting brackets around it is from my knowledge, if I'm correct, the implication in the order of operations comes after the and. So if I did it without brackets, then it would be the integer implies that rational, the x is rational, and this and this. But I want just this to be 1. And then now we're going to make a second thing saying, but some rational numbers are not integers. So basically saying there exists and okay, with the numbers given to us. Yes, I think that I have to use like an and there exists. Like I'll just go. Because there's no but thing in there. This is for all. This is there exists. This is and. This is or. This is not. This is implies. So I'm going to say and there exists an x. I'll say there exists a y. I'm guessing variables are allowed. So there exists a y. But you can't. But the problem is, now that I think about it, is there a symbol for such that? Because normally when you're using these, there exists, you could say there exists a y such that, if y is a rational number, implies like it does not imply that it's an int. But what would you say? some rational numbers are not integers. Because yeah, see, even up here, you have that such that. I'm just gonna try. I'm just gonna try saying that it's just kind of implied and do something else, like saying and there exists y and int. Sorry, no. We're first saying if y is rational. This. This. If y is a rational number. There exists one such if y is a rational number, or others we can just say such that y is a rational number and y is not, that's a is not, an integer. Oh, this is for y. Put that in brackets. Okay, that's my attempt at it. We'll check the solutions afterwards to see how I've done. Okay, the next problem we'll be doing 27. There are some parts here, so I'll be doing 27 as well. So we're referring to the picture of Tarski's world, given example 3.1.13. If you don't know, this is Tarski's world. It's basically just a kind of a visual representation where you can use some of these proof statements, where blue y means that y is blue, triangle x means that x is a triangle, and right of xy means that x is to the right of y. So this is just the model that we'll be looking at, and let's actually see the question. Determine the truth. Right. There's another thing. Let above xy mean that x is above y, but possibly in a different column. Now determine the truth or falsity of each of the following statements. Give reasons for your answers. So first we're going to be doing A. Let's see. For all u, circle, if use a circle implies, or if use a circle, then u is gray. Okay, let us check that. So let's see, if you use a circle, then u is gray. But no, we see this, which I'm guessing is black if these are gray. So the implication that u is a circle does not mean that u is gray. Therefore, we'll say the statement is false because there exists a circle. I don't need to capitalize it. There exists a circle that is not gray. And we'll say that is B. Or we'll say this, B. Okay, let's do another one. What's the second one? For all u, if u is gray, then use a circle. Let's check that. And that's actually true. Look at all the gray ones are circles. So meaning anything gray is a circle. So that is true because all gray objects are circles. There are no counterexamples. Perfect. Okay, let's scroll down again. Sorry for a lot of scrolling. Okay, 28. Okay, let's look at this. In 28 to 30, rewrite each statement without using quantifiers or variables. Indicate which are true and which are false, and justify your answers as best you can. So this seems to be transferring it away from the formal symbolic form into more readable terms, which is a skill that you need to check. Okay, for 28. Let the domain of X be the set D of objects. Basically meaning that of objects discussed in mathematics courses. Okay. So basically saying that x is going to be something from set D. Let real x be x is a real number, pos x be x is a positive number, and neg x be x is a negative number, and int x be x is an integer. So again, we need to indicate which are true, which are false, and justify our answers and rewrite the statements. So first we're doing B. So let's go 28 B. Okay, so this is like for all x, x is a real number and x is a negative number, means that negative x is positive. Okay, so in real terms we're saying, see, if, because that arrow can also mean if, we're saying if or actually, because I'm not going to use x, right? I'm guessing no quantifiers of variables. Yeah, so we're just going to say negative, because I guess we're saying these are negative and real. So all negative real numbers have, and we're saying that this implies that they have a positive what do you call that, a negative value? They have a positive opposite. X becomes negative x. Okay. So, and in my head, that is true. That is true because the negative, or I guess opposite if you use my terms, of a negative number is a positive number. Or we should say of a negative real number. Okay? And I think, what was it, D? Is D the other one that we have to do? Yes, D. There exists x such that x is a real number and x is not an integer. There are numbers such that, we should say there are real numbers that are not integers. So to prove there exists one, we just need to give an example of one. That is true. Any sort of decimal validates the statement. So you can say, for example, 1.5, 2.5 are all, these are real numbers that are not integers. Perfect. 29, there's nothing. 30, there is B over here. So let's write 30B. So it's still in this range of you have to use no quantifiers to indicate which are true and false. Okay, let the domain of x be the set of integers. Okay, let odd x be x is odd, prime x be x is prime, and square x be x is a perfect square. An integer is said to be a perfect square if and only if it equals the square of some integer. For example, 25 is a perfect square because 25 equals 5 squared. Yeah, okay, we all know that. Now B. For all x, prime x, so x is prime, implies that x is not a square. So this is saying all prime numbers are not squares, or I should say perfect squares. There we go, that should work. And that does make sense. It is true, because if a number is square, then it has then how do I say it? It has a factor. Like, it has a factor which would stop it from being prime. The only slight exception would be 1, I guess, because 1 is its own square, but 1 is not considered prime. So it's okay. Okay, next one. 31 is a hint, but not a solution, so let's not do that. Let's do 32 now. Let's write, 32. Let R be the domain of the predicate variable x. Which of the following are true and which are false? Give counterexamples for the statements that are false. Okay. X is more than 2. Sorry, this is implied, not these arrows. I keep saying implies for this one for some reason. Okay. X is more than 2 implies that x is more than 1. Okay. It doesn't say to give any reasoning, so I'll say, yeah, this is true, and it makes sense. Any number is more than 2 is also going to be more than 1. Yeah. The next one is C. X squared is more than 4 implies that x is more than 2. Now, actually, that is false, because don't forget that square roots have technically pairs if you don't actually think about the graph and like it being a function. So we can say, for example, any number less than -2 has a square more than 4. Yeah. Okay, let's do 33 now. Let R be the domain of the predicate variables a, b, and c, and d. Which of the following are true and which are false? Give counterexamples for the statements that are false. Okay. First, a is more than 0 and b is more than 0 means that a, b is more than 0. So basically, if you have two positive numbers, then their product, sorry, I couldn't remember the word. Their product is going to be positive as well, which is true for all numbers. So that is just true. That would be, see here, a is negative and b is negative, means that a, b is less than 0. No, that is actually not true for any numbers a and b, because any negative numbers means that their negativeness will cancel out and make it positive. So it's actually false for all negative numbers. Okay, and that is actually all the questions. Now let's go to the solutions. I know it's going to be around, I think, 858, section 2.3. Let's find 2.5, 3.3, where's 3.2, and here's 3.1, I'm guessing. Now I've done some of these earlier problems, but let's just go to the ones that I've done with you guys. So first, 26. The answer is for all x, int x, if int x, then rational x, and there exists x, rational x, and not int x, which I think that's what we did. Yeah, for all x, if int x and rational x, and I used a different variable, but I think that should be fine as well. Just to be safe, I'll just put this as a note in there that we make these x. So there exists an x, rational x, there exists an x, so that x is rational and x is not an integer. There we go. Now here, as the statement is false because there exists a circle that is not gray, b. False, figure B is a circle that's not gray. True, which I think what we put as well. Then 28b, all negative numbers have a positive opposite. That's true because negative opposite. Yeah, okay. See, if a real number is negative, then when it's, okay, it's 1 ounce among money. If a real number is negative, then when its opposite is computed, the result is a positive real number. The same is true for all real numbers. Yeah, so it's true. And their answer here is there is a real number that is not an integer. I wrote there are real numbers that are not integers. Okay, I guess in my head I knew there was multiple, but I guess for this you shouldn't be aware that this just say 1. That's actually something I'm going to make as a note. Remember to talk in singular terms for where is that symbol for there exists? Just a simple comment, just so I remember that. Okay, 30. We said all prime numbers are not perfect squares. And they said if an integer is prime, then it's not a perfect square. Okay, that's another way of saying it. I basically did it shorter and put it into one clean sentence, but you can write that as well. Now, 32, just said true. Let's see here. Yeah, true, false, true, false. True, false, true, false. And that is it. Thank you for watching. I hope to catch you next time with this wonderful book.